Hi everyone. So now we are slowly moving towards MOSFET amplifiers. We have seen questions on biasing, we have seen MOS physics. Now we are moving towards amplifier. So in the previous videos, what did I tell you? That when we are using MOSFET as an amplifier, we bias the MOSFET in saturation region. And I told you that I will tell you the region later on in the further part of the lectures. Now this is the lecture where I will tell you why do we bias the MOSFET in saturation region while using it as an amplifier. So now we are going to answer that, but before that let's solve a problem that will help us to understand the statement more clearly. So the given question is, this question is slightly based on network analysis only. The given question is, in a two-port network, find the condition of y parameter for which the voltage gain is maximum. Those who don't know y parameter, no need to worry. I will tell you what is y parameter here. I will tell you that. No need to worry about that. Okay. Yeah. So you have to find the condition of y parameter such that your voltage gain is maximum. So let's just assume we apply some source voltage, and that source voltage will have some source resistance as well. This is having Rs, this is the source voltage, and then at the load we are having some output. This is the load where we are having some output. This is a load RL where we are collecting the output. What do we need to do? We need to maximize V naught by Vs. This is what we need to do. Maximize. We need to maximize V naught by Vs. This is our target. What is Y parameter? Y parameter simply shows that your I1 is equals to Y11 V1 plus Y12 V2, and your I2 is equals to Y21 V1 plus Y22 V2. This particular box tells these things. What does this particular box tells? I1 is equals to Y11 V1 plus Y12 V2, I2 is equals to Y21 V1 plus Y22 V2. You have to maximize the voltage gain. You have to maximize V naught by Vs. Now you can replace this particular box with the circuit. How we will replace? Like this. We will replace this particular circuit like this. How did I replace it? Let's check it. What did I say? That your I1 is equals to Y11 V1 plus Y12 V2. Can you apply the nodal here? Can you apply the nodal analysis? If you apply the nodal analysis, what do you see? I1 is equals to V1 is the potential here. This potential is V1. This potential is V1. So what will be the current downward? That would be V1 into Y11 plus the current this side, that would be Y12 V2. Isn't it the same? And what about I2? What about I2? I2 will be Y22 I2. So this resistance is there. Y22 I2 plus this current Y21 V1. Sorry, Y22 not I2, Y22 V2. The voltage drop here is V2. So the current in this direction would be Y22 V2, right? And the current here is Y21 V1. Here the voltage drop is V1. So what will be the current here? The current here will be Y11 V1. So directly you can see I1 is equals to Y11 V1 plus Y12 V2. I2 is equals to Y21 V1 plus Y22 V2. So that's how you can replace the circuit. Are you able to understand this? Okay. Now you need to maximize V0 by Vs. V0 by Vs. You need to maximize this. This is our target. Tell me one thing. If this complete configuration goes to infinite, that means if this complete configuration replaced with the open circuit, what will happen? If this complete configuration is replaced with open circuit, what will happen? Your V1 will be equals to Vs. Your V1 will be equals to Vs. And now this V1 is amplified with Y21 factor. And this complete current is going in the output. Are you getting this point? What I am saying? V1 is amplified with the factor of Y21. And now this Y21 current, Y21 V1, this current will be flowing through this 1 by Y22 resistance and the resistance RL. So first thing is that I need to maximize V1. If my V1 is maximum, then there is high chances that I will get V0 to be maximum, because this V1 is getting amplified. V1 is getting amplified by the factor of Y21. So I need to maximize V1. This is my primary target. Need to maximize V1, and V1 is coming from Vs. So how to maximize V1? If this complete configuration gives you infinite resistance, my target is to get infinite resistance from this complete configuration. How do I get that? How do I get infinite resistance? So my first step is maximize V1. Maximize V1. And for maximizing V1, what do I need to do? So here I was having 1 by Y11, right? 1 by Y11, and this was Y12 V1, I guess. Y12 V2. Y12 V2. And from here, whatever that was coming. So if I make this resistance as infinity, what will happen? V1 will be equals to Vs only, right? V1 will be equals to Vs. If R is infinity, V1 will be equals to Vs. How you can make R equals to infinity? Tell me. How you can make R equals to infinity? Y11 goes to 0 and Y12 also goes to 0. If Y11 goes to 0, what will happen? This resistance value will be infinity. What do you mean by infinite resistance? What do you mean by infinite resistance? Open circuited. If Y12 goes to 0, that means this current will be 0. What do you mean by 0 current? Open circuit. In open circuit, there is no current. In short circuit, there can be current. But in open circuit, there will be 0 current. So if Y12 is 0, that means there will be 0 current. That means this is open circuited. So from here you see infinite resistance. Are you getting this point or not? So my desired condition came out to be Y11 and Y12 should be 0, or you can say both should be minimum. So Y12 should be minimum and Y12 should be minimum. If not 0, they should be minimum. So this is the desired condition. So first condition we have found, that is our Y11 and Y12 should be minimum. Did you understand? My target was to maximize V1 because V1 is getting amplified here. So how do I maximize it? By making the resistance infinity. How do I make the resistance infinity? If I put Y11 equals to 0, that means the resistance will be infinite. And if I put Y12 equals to 0, the current source will be 0. If current source is 0, that means infinity resistance. So infinite parallel with infinite is equals to infinite only. So I made Y12 equals to 0 and Y11 equals to 0. Or this is the ideal condition. Practical one is that both should be minimum. So then only you will get V1 equals to Vs. Now what is my second target? My second target is this Y21 V1 current is going in two resistances, that is RL and 1 by Y22. This 1 by Y22 resistance, this particular resistance is eating up some current. This particular resistance is eating up some current. This is eating up some part of Y21 V1. If this resistance is infinity, then what will happen? If 1 by Y22 is infinity, what will happen? The complete current will be flowing through RL. Are you getting this point? If 1 by Y22 is infinity, or if Y22 is 0, that means the complete current will be flowing through RL. Say yes or no. Right? Then what will be your V0? V0 will be Y21 V1 into RL, and minus sign will be there because this current will be flowing like this. Did you understand this point? So my second target is maximize V0. Maximize V0, or you can say minimize Y22 V2. Minimize Y22 V2. This current you need to minimize, or minimize Y22 V2. Then what is the target? That your Y22 should be 0. From here we got to know that Y22 should be 0 or Y22 should be minimum. So we got to know about y11, y12, y22. Now the only thing left is that is y21, y21, y21. So now what is your V naught? Your V naught is simply this current, y21 current. This resistance is infinity. So the complete current is flowing through RL. So what is your V naught? V naught is y21 V1 into RL and minus sign. Y21 V1 into RL and minus sign will be there. That is your V naught, because this current is flowing like this, right? Y21 V1 into RL and minus sign will be there. That will be your V naught. This is first equation I can say, and one more thing I can say is that V1 is equals to Vs. So what is your gain? Gain is minus y21 RL. This is your gain. To have the maximum gain, what should be the condition? To have maximum gain, y21 should be maximum. That's it. We have found all the condition. What are the all the condition? Y12 minimum, y21, okay, y12 minimum, y11 minimum, y12 minimum, y22 minimum. Only maximum is y21. Y21 is maximum. That's it. These are the condition. Are you getting this point? When you see this structure, you don't need to think much. How you will think? You will think that okay, the I1 current is coming. I1 current is coming. Forget about I1 current. I need to maximize V1. So how do I maximize V1? That Y11 is 0, Y12 is 0. If both are 0, that means we will see infinite resistance. Then V1 will be equal to Vs. So Y11 and Y12 has to be minimum. Now this V1 is being amplified by the factor of Y21. Now if this is amplified, the amplification should be large. V1 is being amplified with the factor of y21. If it is being amplified with the factor of y21, that means the amplification will be should be large. If amplification is large, that means I will have more output. So for that, y21 should be large enough. So y21 should be maximum. Y21 should be maximum. And what about y22? This y21 current is flowing through two paths. The two paths are the resistance 1 by y22 and the other resistance RL. So now this current should flow through only RL. This Y12 1 by Y22 resistance should not eat up any current. So the complete current will be flowing through RL. So for that, your Y22 should be equals to 0. That means Y22 should be minimum. So by this we have found all the condition. This is the most important part. This is the most important output that we have received. Now let's copy those equations again and find out what is our y11, what is our y12, what is our y21, and what is our y22. So tell me what is y11. What is y11? Y11 is delta I1 by delta V1 with V2 being constant. Do you agree with this? Y11 is delta I1 by delta V1 with V2 being constant. If V2 is constant, then what will be your y11? That would be delta I1 by delta V1. Just differentiate it. Delta I1 by delta V1. This will be 1 and V2 is constant, that will be 0. So what you will get? Y11 only, right? So I will make a small two-port network here. This is our V1. This is our I1. This is our V2. This is our I2. So what is our Y11? Y11 is V1 by I1 by V1. I1 by V1 with V2 being constant. What is our Y12? Tell me. What is our Y12? Y12 is I1 by V2, delta I1 by V2, delta, I should put delta here. Yeah. So that is y12 is delta I1 by delta V2 with V1 being constant. If V1 is constant, this differentiation will be 0. This will be delta I1, this will be delta V2. So delta I1 by delta V2 is equals to y12. Delta I1 by delta V2 with V1 being constant. What about y21? What is y21? Y21 is delta I2 by delta V1 with V2 being constant. Delta I2 by delta V1 with V2 being constant. You can write it. What will be y22? Y22 will be delta I2 by delta V2 with V1 being constant. Very easy, very simple. Okay, let's not do it. These are the input parameters only, delta I1 by delta V1, delta I1 by delta V2. What do you think this is? What do you think? What is this? If I say this is my output port, if I say this is my output port and this is my input port, right hand side is output, left hand side is input. So if this is my output, this is my input, then what does delta I2 by delta V1 represent? Everyone should be able to answer. What does delta I2 by delta V1 represent? This represents transconductance. Output current, change in output current with respect to the change in input voltage. So this is transconductance. This is GM. I will simply write GM. You will be able to understand. What is delta I2 by delta V2? What is delta I2 by delta V2? That is output, not output resistance. It is 1 by output resistance. 1 by output resistance. Are you getting this point? Delta I2 by delta V1, delta I2 by delta V2, delta I2 by delta V2 at output only. We have calculated both of the parameter for MOS. GM also we calculated, output resistance also we calculated. For saturation region we calculated, for triode region also we calculated. Now this thing only we have to use because a MOSFET is also a two-port network only. This is also a two-port network only, right? I guess I can give a light color. इतना भी नहीं जाना भाई, ठीक है. Isn't it a two-port network? What is the input parameter? That is VGS. What is this output parameter? That is VDS. We call this as I gate. What is I gate? 0 ampere always. I gate is 0 ampere always. And what is this? We call this as I drain. I drain. So for both triode and saturation region, for both triode and saturation region, delta Ig by delta VGS. Here I should write capital VGS, not small. Delta Ig by delta VGS. What is delta Ig by delta VGS? That is delta I1 by delta V1. Delta I1 by delta V1. What is delta I1 by delta V1? That is Y11. Y11 is equals to 0. Why it is 0? Because Ig is 0 ampere. Ig is 0 ampere. So no point of differentiation. If the current itself is 0, there is no point of differentiation. So Y11 is 0. And what about this factor? Delta I1 by delta VDS. That means delta Ig by delta VDS. Input current and divided by output voltage. This is also 0. That means Y21. What is this? This is Y12, sorry. Y12 is also 0. And this is what we needed. We needed Y11 and Y12 to be minimum. And this is what we needed. And that is satisfied. for both of the region. For both of the region, it is satisfied. This is also we needed. This is also we needed. Now talking about GM. Now these two are the deciding one. Whether we should go for triode region or saturation region. So these two are the deciding one. So what do you need? You need Y21 to be maximum. Y21 to be maximum. That means you need transconductance to be maximum. So now we are going to compare the transconductance of a triode region and saturation region. So delta VDS versus output current divided by input voltage. So delta ID by delta VGS for saturation and triode. We are basically comparing the GM. So GM of triode. What is the GM of triode? GM of triode is mu n COX W by L VDS. This is the GM of triode, right? You write down the current expression. You need to differentiate it with respect to VGS. So VDS square by 2 will be 0 only because differentiation will be 0. VGS minus VT will be 1 only and VDS will remain there. So this is the GM of triode region. In case of triode region, VDS is less than VGS minus VT. That means VDS is very low. Also you can see by curve as well that in case of triode, this is our triode region. So this was ID versus VDS. So in triode region, VDS was very low. Here was your VDS. So VDS is very low. So if VDS is very low, that shows that GM will be very low. GM will be very low. So GM of triode region is lesser than the GM of saturation region. Now why the saturation region GM is high? GM will be very low in triode region. In triode region. Right? Let's give this line a highlight because we are comparing both of the values. Now what about the GM of saturation region? GM of saturation region. What will be the GM of saturation region? Mu n COX W by L VGS minus VT. That's it. Just a second. So this is the GM. Now how can you comment whether this will be a large value or low value? How can you comment? How will you comment? Let's write down the ID saturation current. What is your ID set? ID set is mu n COX W by 12 VGS minus VT whole square. So here ID and VGS follows square law relation. Here ID and VGS follow square law relation. Square law relation. That means the slope will be high. Slope, what is the slope? That is del ID by del VGS will be high. How do I comment on that? Let's make a graph. ID versus VGS. So in case of saturation region, ID versus VGS follows the square law relation. So this will be the slope. This will be the slope. So let's just assume if one is y equals to x and the other function is y equals to x square. What is the differentiation of this? What is the slope here? That is 1. And what is the slope here? That is 2x. Now what if my x value is 2? So my slope will be 4. So if it is following square law relation, there is high chances that slope will be larger. If it was following cubic relation, what will be the square? 3x square. If my x value is 2, then what will be the slope? Slope will be 2, 4, 12. So if it is in the higher power, that means the slope will be larger. Are you getting this point? So ID, in case of saturation region, the relation between ID set and VGS is square law. But in case of triode region, what is ID? In case of triode region, what is ID? Some Kn, then VGS minus VT into VDS minus VDS square by 2. So here the relation is not square, here the relation is linear. So that's why the slope will be lesser. But in case of saturation region, the relation is square. The relation is square law. Okay. And follow square law relation, or you can say square relation, whatever you can write. So in case of saturation region, the relation is square. In case of triode region, the relation is linear. So since it is square relation, the GM of saturation region will be larger. So here you conclude that GM of saturation region is larger than GM of triode region. So this is concluded. And what do we need? We needed high GM or lower GM? Let's check. We needed this value y21 to be larger. We needed y21 to be large. We needed this one to be large. So we needed GM to be large. And where are we getting GM large? We are getting in saturation region. So this is one of the advantage. If we are running our transistor in saturation region, we get large GM. If we are getting larger GM, that means we can have higher gain. So this is one of the advantage. Now let's check the final parameter. Here we checked these two parameters. Here in both of the region, both of the parameters were same. So we cannot conclude. Then we checked this parameter, GM we checked. So by checking the GM, we got to know that we have advantage in saturation region. Advantage in saturation region. Now let's check the final parameter, that is del ID by del VDS. Del ID by del VDS for linear and saturation region. Linear and triode are one things only, right? Both are same. I have told this thing again and again. Linear and triode both are same only. So what is del ID by del VDS for linear region? That is del ID by del VDS. That is linear. In linear we can check, or in deep triode we should check. Deep linear we should check, right? Because we wrote the expression for deep linear, not for linear. So we can write the expression for deep linear. That is mu n cux w by L VGS minus VT. Right? Yeah, correct. And what about del ID by del VDS in saturation? So there were two answers. One was lambda ID set if lambda is not equals to 0, and if lambda is equals to 0, it was infinity. If lambda is equals to 0, it was infinity. So there were two answers. Or simply by the waveform also you can check. What was your ID versus VDS? We are checking at the output only. So now we will draw ID versus VDS. ID versus VDS. So we have drawn the ID versus VDS previously as well. How does it look like? It looks like this. Or there are two chances, it can go something like this as well. This is linear, this is saturation. Here you can directly see that this is the slope. Let's call this slope as theta 1 and let's call this slope as theta 2. Theta 2. So here you can directly see that theta 1 is larger than theta 2. That means in linear region the slope is larger. The slope is larger. And in saturation region the slope is less. The slope is less in saturation region. That means the output resistance is high. What you are saying that delta ID by delta VDS is less. This is less. That means delta VDS by delta ID will be high, right, for saturation. So in saturation region you are getting high value of output resistance. What you can conclude, here you can see for saturation region output resistance is high. And what did you need? You need output resistance to be high or low. Let's check here. You needed Y22 to be 0. You needed Y22 to be minimum. That means you needed Y22 to be 0. That means you needed output resistance to be high. Did you understand this point or not? In case of saturation region, what did we get to know? We get to know that our GM value is larger. In case of saturation region, GM value is larger than triode region. If GM value is larger, then that is our advantage because we wanted GM value to be large. We wanted that current source to be large, but output resistance to be as minimum as possible. We wanted our output resistance to be as minimum as possible. And output resistance should be as maximum as possible. Sorry for that. We wanted GM to be large and output resistance to be large as well, so that the output resistance doesn't eat up any current and all the current goes into the load. If output resistance is large, if this resistance is large, if this resistance is large, it will not eat up any current and all the current will go into the load. This is what we wanted. And in case of saturation region, we got output resistance to be large, also we got GM to be large. That's why we conduct a MOSFET in saturation region while we are using it as an amplifier. When we use the MOSFET as an amplifier, we use it in saturation region. So this is the answer. What will be your answer if in the interview they ask you, why do, like in the interview they are not expecting you this much of analysis. This much of analysis was there just to make you understand. So in the interview you can directly say that, sir, for an amplifier I will need a higher GM value, a higher transconductance and lower output resistance. So in case of MOSFET amplifier, when we are running in saturation region, we get to see that our value is also higher and our output resistance is also higher. So in case of saturation region, GM value is higher than the triode region, and in case of saturation region, output resistance is also higher than the triode region. So that's why we use MOSFET as an amplifier in saturation region. That's it. So why we use MOSFET in saturation region for amplification? Because in saturation region we get higher GM and higher output resistance that maximizes our voltage gain. That's it. Understood? So this is the reason why we use MOSFET as an amplifier in saturation region. So this was a very famous interview question. Even in the even in GATE 2023, this kind of question was asked, but in this form, in this Y parameter form. Although every time when I deal this course, whenever I teach analog electronics, every time I deal this question, and this kind of question was asked in GATE 2023 as well. They wanted to test your concept that if you know how to find the maximum gain. So for getting the maximum gain, the resistance here should be the minimum. So y11 should be 0, y12 should be 0. And now it is being amplified, so amplifying factor should be large. Y21 should be large. Now it is going into two resistances, so the other resistance should be large, so that it doesn't eat up any current. So y22 should be 0, so that the resistance becomes larger and all the current goes into the load. The same thing is happening in the MOS. In the MOS, for both of the region, for both triode region and saturation region, the input parameters are 0 only. So no worries about that. Let's talk about the output one. So let's talk about the GM. So GM in that triode region was lesser than the saturation region. So in triode region, GM was less, but in saturation region, GM was more. So this was one of the advantage. Then in case of linear region, your output resistance was lesser, but in case of saturation region, your output resistance was more, because here the slope is larger. If the slope is larger, that means output resistance is low. But in case of saturation region, output resistance is larger. So if output resistance is larger, that means the output resistance will not eat up any current, and most of the current will go through the load only. So that's it. So that's why we use MOSFET in saturation region for amplification. This is one of the most important answer for your interview, and even for the GATE examination, because they can ask any question, right? Let's move on to the next concept. Now we have understood that we have to bias the MOSFET in saturation region. We have understood we have to bias the MOSFET in saturation region. Now how we will bias it? This is our target now. I have the MOSFET device with me. I have resistances. I have the battery. Now how will I bias it? So we are trying to bias the MOSFET. This is our first try. So will this try work? Let's check that out. Let's check out, will this try work? So what I have done here, I have given some DC voltage and superimpose AC there. I told you we will give DC supply as well, we will give the biasing as well, and then we will give the AC. So both I am giving here at the gate, and at the load I am having V naught. So here I am expecting my output. This is the output I am expecting. So this is my try one. Will that work? Let's check. Let's assume my VG is 3 volt. This Vs can be anything. It can be 20 millivolt sin omega t. Okay. Let's assume my Vt is 1 volt. This is I am assuming. So for saturation region, what do you need? 1 volt. For saturation, what do you need? Your VDS should be greater than VGS minus VT. So your VDS should be greater than, what is your VGS? VGS is 3 plus 20 millivolt sin omega t. 3 plus 20 millivolt sin omega t. This value will be nearly 3 volt only, right? Nearly 3 volt only. 3 plus minus 20 millivolt. 3 plus 0.2 and 2.98. So it will be nearly 3 volt only, right? So no need to worry about it. This is nearly 3 volt only. Minus Vt, that is 1. So you need your VDS to be greater than 2 volt. This is what you need. Now let's just assume if my transistor turns on. If my transistor turns on, what will happen? There will be some ID current flowing through it. If my transistor is on, there will be some ID current flowing through it. Then what will be your VDS value? VDS value will be minus ID into RL, which is negative. VDS value will be minus ID into RL, which is negative. You needed VDS to be greater than 2 volt. You needed VDS to be greater than 2 volt, but here you are getting VDS to be negative. So this is not desired. Not desired. So if you use this configuration, what will happen? Your transistor will not even turn on. The transistor will be in cutoff. So MOS will be in cutoff. If you use this configuration, MOS will be in cutoff. So it will not even turn on. So this is the disadvantage here, that you are not able to turn on the transistor. Are you getting this point? So now we have to make another try. So now what I am doing, I know one thing, my VGG is 3 volt only, my Vs is 20 millivolt sin omega t, right? So what VDS I need? VDS should be greater than 2 volt for saturation region. By this condition, I found out that my VDS should be greater than 2 volt. This I know. This I know, my VDS should be greater than 2 volt. So what did I thought? I thought that, what did I think? I thought that I should fix VDS value. I need VDS value to be 2 volt. So I will fix it here. I will connect a battery of 2 volt. So I have fixed this. This is 2 volt battery I am connecting. So here, okay, you need greater than 2 volt. So let's assume I am connecting a battery of 2.5 volt. Here VDS is greater than VGS minus VT. So saturation is there. Saturation is there. But what is wrong happening here? What is wrong? We needed saturation region, and here I have ensured that I get my saturation region. But what is wrong here? In this configuration, what is wrong? Output is fixed. V naught is equals to 2.5 volt, which is fixed. Output is fixed, bro. But you needed the amplifier, you needed the MOS as an amplifier. So how you are saying that it is working as an amplifier? If output is fixed, how it is an amplifier? Output is fixed. That means it is not working as an amplifier. Not working as an amplifier. So this biasing is also not considered. This biasing is also wrong. In the first one, what did we get to know? We got to know that VDS is negative. And if VDS is negative, your MOS will be in cutoff. So this biasing is eradicated. This biasing is also wrong. This biasing is wrong. Why this is also wrong? Because here you have fixed the output. So what happened to this 20 millivolt sin omega t? Is that amplified? No. At output you are having fixed voltage, that is 2.5 volt. And already you are having a battery of 2.5 volts. So why do you need this MOSFET? What is the use of this MOSFET here? There is no use of this MOSFET, right? You are not even amplifying the voltage. You needed the MOS as an amplifier. So you are not even amplifying the voltage. So now I did this thing. I tried the third one. So here my output is not fixed. Here my output is this one. So this is my output. But tell me, what is the value of VDS here? Let's just call this one as 3 volt again, 20 millivolt sin omega t, with VT being same 1 volt. Now in this one, what is my VDS value? VDS value is VDD minus IDRL. Now you can adjust VDD. You have the liability to adjust the VDD such that your MOSFET works in saturation region. You can adjust VDD such that your MOS works in saturation region. Works in saturation region. So now you have the liberty to change your VDS value. So now you can change your VDS value. Also, your output is not fixed. Also, output is not fixed. So this biasing technique can be used. But again, there are some issues with that. What is that issue? That we will learn when we are studying common source amplifier. But here briefly I can tell you what is that issue. The issue is two batteries. One battery is VDD, the other battery is VGG. So you don't want to use two batteries. You have only one supply. With the help of VDD supply only, you have to bias the gate voltage as well. For drain voltage, you are using VDD. But it's not that for gate voltage I will use another supply. When you make a chip, only one of the supply will be given. You either have 5 volt or 2.8 volt or 1.2 volt or 1.6 volt, but you will have only one supply. With the help of that supply only, you need to generate other supply. Let's assume I am having 5 volt. I am having 5 volt supply. I am having 5 volt supply, but I need 2.5 volt somewhere. How will I generate that? Voltage divider. I have 5 volt, R and R voltage divider, I will get 2.5. If I need 3 volt, how will I do that? I need 3 volt. So I will do 2R, 3R. Voltage divider again, 2R, 3R. And on upper side, I am having 5 volt. So 2R, 3R, here I will get 3 volt. So with the help of one supply only, you have to generate other supply. Are you getting this point? So again, this biasing has some issue, but for now, let's just accept it. When we study deep analysis of common gate and common source amplifier, we will see that biasing technique. But for now, let's just accept this biasing technique. Well and good. So this biasing technique is accepted for now. So we have biased the MOSFET now. Now we are going to do the small signal analysis of MOSFET amplifier. So basically, now we are going to study the small signal analysis of MOS amplifiers. So this structure cannot this structure can be replaced with something like this. Can't it be replaced with something like this? इसको ऐसे लिख सकता हूँ ना मैं. This is VDD, then I am having RL, then I am having the MOS. Look, this potential is 0, this potential is VDD. Then from VDD, RL is connected. Then at RL, here you are having the output. This is your output V0. Then you are having the MOS. The source is grounded, and here this is the input. This input we can call Vi. Vi is equals to VGG plus Vs, VGG plus Vs. So generally you will get this kind of configuration, not this kind of configuration. They will not make this big structure. They will just show it something like this. VDD, RL, V0. At Vi you are having VGG plus Vs. That's it. So this is how they will make it in the examination or in the question paper. You will see this kind of circuit only. So we will also deal this kind of circuit only. So this is our circuit. Simply VDD, RD, V0, VGG plus Vm sin omega t. So this is our input. So what is our input? This is the DC supply and this is the AC. This is DC and what is AC? AC I am calling small VGS. The AC input that I am having, this I am calling small VGS. Basically my small VGS is Vm sin omega t. Small signal AC input. Now I will generate some ID. Now this ID is DC quantity or AC quantity, that I don't know. I will just simply write down the expression, then you will get to see something very interesting. So just hold on to the video till the last. So I will write the ID expression now. What is the ID expression? Mu n COX W by 2L. Also I am considering MOS to be in saturation region. I have adjusted my RD value and VDD value such that my MOS is working in saturation region. So I am considering MOS to be in saturation region. So I will apply the current of saturation region only. So mu n COX W by L VGS minus VT whole square. So what will be my ID? Mu n COX W by 2L. What is my VGS? VGS is VGG plus Vm sin omega t. VGG plus Vm sin omega t minus Vt whole square. So can I write it down something like this? ID is, I will again write down the expression. mu n cux w by 2l vgg minus vt square. I am writing vgg minus vt plus vm sin omega t plus vm sin omega t. Can I take out this much expression? If I take out this much of expression, what I will get? Mu n cux w by 2l. I am taking out vgg minus vt whole square. Vgg minus vt whole square. So I will be left with 1 plus vm sin omega t divided by vgg minus vt whole square. Till this point, are you guys able to understand? You guys are able to understand, right? vgg minus vt I took out. You can take it inside as well. You will get the same thing, right? Well and good. ये एक्सप्रेशन समझ में आया ना? vgg minus vt को बाहर लिया, यहीं पे बाहर ले लो तो 1 plus vm sin omega t by vgg minus vt. So vgg minus vt whole square is getting out, and this is what we are getting. So this is the ID expression we are getting. Now one thing I know, this is very small. This is very small, right? Why it is small? Because this is a small signal. Vm sin omega t is a small signal. So this particular quantity is very small. And one thing I know, that is 1 plus x square, x whole square can be approximated to 1 plus 2x if x is very small. If x is very small, this we can do. So ID is equals to mu n cux w by 2l vgg minus vt whole square into 1 plus 2 vm sin omega t vgg minus vt. Now people will say that sir, why you are doing the derivations? This is not important for gate. But if you just understand the small signal analysis, okay, just short circuit the DC bias, just open circuit what do we say, just short circuit the capacitor, do this, do that. There is no meaning of that. There is no meaning of learning the things like that. Here I am not eating up your time. There can be other irrelevant things too, but that I am not teaching. But this is relevant to gate. If you don't know these much of concept, like from where small signal analysis is coming, then some other day they can frame a very good question where this concept will be used. From where the derivation of small signal analysis is coming. Why do we short circuit the DC bias? What is the actual need? Here I did not short circuit anything. I am just applying the simple formula. That's it. Nothing I am doing. Simple formula I am applying. We have VGG, we have VM sin omega t. Simple formula we are applying. That's it. We are going with the simple analysis, right? So what is the ID expression you are getting? What do you think what this is? Mu n cx w by 2l vgg minus vt square. What do you think what this is? If in the input I only had the DC supply, if I only had the DC supply, what would be my current? If in the input, if I only had the DC supply, what would be my current? My current would be mu n cx w by 2l vgg minus vt square. So I can write down this is DC current, right? This is DC current if my input had only VGG supply. If my input had only VGG supply, my current would be mu n cx w by 2l VGG minus VT whole square. So I will write down this is IDC. This much expression is IDC. Current if only VGG was applied. VGG, or in bracket I can say DC was applied. This is my IDC, and then I am having 1 plus 2 Vm sin omega t VGG minus Vt. Now what I can write, ID is equals to, now this IDC can go inside, IDC into 1 plus IDC into this factor. So it will be IDC plus 2 into IDC VGG minus Vt, 2 into IDC VGG minus Vt Vm sin omega t. Now tell me what is this expression? Those guys who have studied seriously, they will be able to tell what is this expression. What is this expression? This is GM. This is transconductance. What is transconductance? Transconductance we have studied 2IDC by VGS minus VT. If I did not apply any AC signal, if I did not apply any AC signal, my VGS would be VGG only. If I did not apply any AC signal, then this VGS would be VGG only. So this will be my transconductance. So this expression 2IDC by VGG minus VT is transconductance only. Are you getting this point? So now what you are able to replace with? ID is equals to IDC plus this is the transconductance GM into VGS. Why VGS? Because at the first page I wrote that small signal Vm sin omega t, I am replacing it with VGS. GM VGS. VGS is Vm sin omega t, which is small signal AC input. Small signal AC input. So here I got to know that in my ID expression, what I am getting? I am getting a DC component. I am getting a DC component, and along with that, in the addition, I am getting AC component. Are you getting this point or not? And what about V naught? What will be your V naught? Tell me. What will be your V naught? V naught will be VDD minus IDRD. V naught will be VDD minus IDRD. That would be VDD minus, what is ID? ID is IDC plus GM-VGS into RD. What do you get here? VDD minus IDC into RD minus GM-VGS into RD. Again in the V naught, what do you see? This much expression is DC component and this much expression is AC component. So what did you understand? Why this is DC component? If I had not applied any AC signal, if I had applied only DC signal, that means if my current was only DC, then what would be my output? Output would be VDD minus IDC into RD. So every small signal I am denoting by small value GS. VGS is small. So that's why I am saying this is small signal. Like at many times you will find this VGG as written as VGS, capital VGS. But here I have wrote VGS only, VGG only. Yeah. So what I was saying, if there was no AC signal, this would be my output. And this I can say my DC output. So this is my DC output. And what is my AC output? But here I have applied both signal DC and AC. What is my AC output? My AC output is coming out to be minus GM VGS RD. In my final AC output, my AC output is, what is my AC output? V naught AC. V naught AC. That is minus GM VGS RD. And what is my ID AC? ID AC. That is GM VGS. Now both of the expression does not have any DC component. Are they having any DC component? Are they having VDD? Are they having VGG? VGG is a DC component, VDD is a DC component. Are they having those component in their final output? Here, both of them are, I can replace it somewhere here. Here, what we see is that both of them are not a component of DC, or we should not write, we should write like that, not a component of VDD or VGG, not a function of VDD or VGG. That's why we say that while doing the AC analysis, we can short circuit the DC supply. Why so? Because by the detailed analysis, what did we get to know? We got to know that in the final current, there are two expressions, DC current and AC current. In the final output as well, there are two expressions, DC voltage and AC voltage. both AC voltage and AC current doesn't have any AC component. And what about DC component? This is the DC component. DC component is IDC, and this is the DC component. DC component is also not having any AC component. So here you got to know that both AC and DC components are independent. Although they are dependent, how they are dependent? Because if you are not even biasing, if you are not even giving the DC supply, there is no meaning of applying the AC signal. If you are not giving the DC supply, there is no meaning of applying the AC signal. This we covered in lecture 1 only. Because if you just apply AC signal, you will not get any output because transistor will not even turn on. So for turning on the transistor, I have given the DC signal. Once the transistor is turned on, once the transistor is working in saturation region, now I can apply my AC signal and that will be amplified. So here we are not actually applying superposition, but it is acting as if we are applying superposition. So what is the conclusion of this? That you can apply superposition. How you can apply superposition? So we will come on to this part later on, but let's just see this. So by whatever that we have done previously, from here you can break your MOSFET in two components, DC and AC. So this we call actually DC analysis, and this one we call actually AC analysis. So in DC analysis, what do? We will only consider DC sources, because in the DC output, what we have seen, in DC output only we are having DC component, and here also we are only having DC component. So we will not consider any AC component here. So VDD is the DC component. Okay, VDD will be there. RD is the simple resistance, no meaning of DC AC. Then this is the simple MOS we are having. Then at the input, I will only consider VGG, and this is my output. That's it. And in AC analysis, what I will do? Will I make VDD here? Will I make VDD here? No. Why I am not making VDD here? Because in the output, I am not getting any VDD component. Then this is the MOS I am having. Here I will write Vm sin omega t, only the AC signal, and this is my output. I will have a small id. This I am calling small id only. No, this GMVGS I can call it small id. Okay, I generally call it small id. Small id. This is the AC signal. So small id. What will be my V naught? V naught will be minus small id into RD. What is small id? Small id is GMVGS. GMVGS into RD. So finally I made this circuit, and what did I get to know? That simply using this circuit I can do my circuit analysis. But this biasing will not work. If I am not giving any DC supply, this will not work as a transistor. This will not work as an amplifier. If I am not giving any DC supply, it will not work as an amplifier. We have to give DC supply. But after giving the DC supply, after imposing the AC signal, we did the current domain analysis. We wrote the expression of current, then we did the analysis, then we got to know that we can break down our circuit in two parts. So for analysis purpose, this is done only for analysis purpose. Only for analysis purpose. So I will write for analysis purpose. So this is how you can analyze for analysis purpose. So every time you cannot write current expressions, right? Every time you cannot write these current expressions. So how will you analyze the circuits? The circuit will be given. First you will do the DC analysis. After doing the DC analysis, what you will get to know? You will get to know the value of GM. You will get to know the value of GM, because what is GM? GM is 2 IDC divided by VGG minus VT. So from here you will get to know GM, and then you will do the AC analysis. From AC analysis you will get to know the final output V naught, and that is minus GM VGS RD. So VGS you already know. VGS is, this is your VGS. VGS is Vm sin omega t. GM also you know. GM is 2 ID by VGG minus VT. That you got to know from DC analysis, and RD value also you know. So then you can write down your gain. Are you able to understand this complete analysis? This everything that we have studied in MOSFET amplifier till now. What we studied? Let's start from the beginning. So in the beginning, we saw that why we use the MOSFET in the saturation region for amplification. Then once we got to know, then we biased the transistor. We tried biasing. This was our first try. Here the transistor was turning off. This was going into cutoff region. We tried this one. Here we fixed the output voltage, which is not desirable. Then we tried this one. Here we can change the VDD value as per our requirement. VDD value as per our requirement. So we can bias the transistor in saturation region. So this we have accepted. So once we accept it, then we do the small signal analysis. That large and small signal analysis both we are doing. Actually, I should not write small signal analysis. I should write large and small signal analysis. Both analysis we are doing. We are also considering the DC source. We are also considering the AC source. Then we considered both of them. Then we got to know this is the ID expression we are getting. Then in the ID expression, we are having both DC and AC component. So then we got to know that AC component is not having any DC part and DC component is not having any AC part. So you can break down your transistor for analysis purpose. You can break down your transistor in two parts like this. If you can break down your transistor in two parts like this, so in AC analysis, you will not consider any DC source. And in DC analysis, you will not consider any AC source. By DC analysis, first you will find the value of GM, and then by using this GM, you will get to know the V0 values. Are you able to understand this complete analysis? Now, everything we did here, this much of equations we have applied, all these things we did here, we could understand it with the simple graph as well. How could we understand? This is our input, VGS is our input. VGS is our input. This is VGS, which is our input. Input is some DC supply plus superimposition of AC. So this is the DC supply plus superposition of AC. Let's assume my input was VGS was VGG plus Vm sin omega t. So let's assume it was some 2 plus 20 millivolt sin omega t. So this is what we were doing. And with respect to this, we will get this output. This is the ID we will get. This is the ID we will get. So in this is the final ID. In this ID, what you can see? In VGS, we have DC signal and AC signal. In the final ID, what you can see? It has some DC. This is the DC. This is the DC level, and it has some AC as well. So in the output here, you can see this is a combination of DC plus AC. DC plus AC. How can you find the AC signal? AC signal, and this I am calling as VGS. How you can find the AC signal? What you will do? You will find the slope at operating point. What do I mean by operating point? You will find the slope at operating point. This is the slope that you will find. This slope. Let's call this slope as theta. So your theta will be del ID by del VGS. At operating point you are finding. What is operating point? Operating point is this DC value, VGG. This point is VGG only. This point is VGG. So at operating point, at VGG, you will find this value. That is your GM only. So you will find this GM. If you multiply GM with VGS, what do you get? GM with small VGS, what do you get? ID. You will get AC output current. What I am saying, you find the slope and then you multiply that slope. That slope is GM only. You multiply that slope with VGS. What do you get? You get the AC output signal. Look, this ID is having IDC, which is DC, plus some AC signal. DC value you will get. By VGG, you can get the DC value. But the thing is how we will get AC output. So for AC output, you get the slope on this point. Because this point, and this point, all are very nearer. All these points, these 3 points are very near. 20 millivolt is a very small quantity. So all are very near. So at that particular point, you find the value of slope. That slope gives you del ID by del VGS, that is GM. If you multiply GM with VGS, if you multiply GM with small VGS, this small VGS, you will get the AC signal. So this AC signal would be GM into this small VGS. You find the slope and then you multiply this magnitude. This is VGS. This is your VGS. You found the slope and you multiply with VGS. That will give you the AC output. Are you getting this point? And this we call small ID. If you did not understand by this analysis, there is no need to worry. This analysis is also good enough. But you don't need to remember this analysis. Just you need to understand one simple thing, that is, if you see any configuration, you can break it down in two parts, DC and AC. Now you will not call this as superposition theorem. I have seen many educators calling this as superposition theorem, that you are applying superposition theorem. That is completely senseless. This is not superposition theorem. When we write down the expression, we got to know that we can break it in two parts, DC and AC part. So for analysis purpose, I can separately treat DC analysis and I can separately treat AC analysis. So in DC analysis, I will not consider any AC part, and in AC analysis, I will not consider any DC part. So this is how I can break it down. Are you able to understand? And this analysis, I will again tell, at one particular point you find the slope, that is GM. If you multiply the GM with VGS, what do you get? You get the output AC current. That's it. Are you getting this point? The slope into the y-axis value. Sorry, the slope into the x-axis value. What it will give you? Y-axis value. Slope into x-axis. What is slope? Slope is y by x into the x value. It will give you y-axis value. That's it. So slope into the AC signal will give you output AC signal. Slope into input AC signal will give you output AC signal. This is what we are getting. So your output current is GMVGS. That you need to remember. Your output current is GMVGS, where your VGS is small signal AC input. Are you able to understand this point? Now we will see the small signal model of MOSFET. So then we will see the small signal model of MOSFET, and then we will see the small signal model of NMOS and PMOS. And then we will see the concept of port impedance, and after that we will move on to common source amplifier. So these things are left to study. I thought I will be able to cover it up in this lecture only, but I don't think I will be able to cover it up. So in the next lecture, we will see the small signal model of MOSFET in case of PMOS as well, in case of NMOS as well. And in one line only, you will be able to solve every configuration in one line. This is my guarantee, in one line. So just you are watching the lectures from beginning. So I hope you are understanding what kind of depth we are covering. So in one line only, you will be able to understand all the circuit. You will be able to understand the complete language of the question, right? So let's meet in the next lecture. We will study a lot of things. Thank you.